Okay, so today I'm going to start a new chapter from the book that is known as Linear Models for Regression, and it will lay the foundation, and somewhere we're going to connect all those concepts what we have discussed so far in our previous classes. And it is one of the fundamental concept in machine learning where all other models will be like somewhere going to connect with these fundamentals. So please pay attention. All things are not new. We will be taking few things that we have already been discussed, but in more formal way with more derivations, mathematical derivations, and try to like put the foundation for the upcoming lectures, right? So you know what so far we have discussed like polynomial curve fitting model. So what is polynomial curve fitting? That is also a specific class of linear basis function models. Uh, what we have discussed so far is just a specific case, right? So in general, these models are known as linear functional models or linear basis function models. I will clear you this what basis means. So in short, if I give you this, can you see this color also here now?
Yes, sir.
My pen is visible to you what I'm doing now, right?
Yes, sir.
Okay. So this is like in general, this is what you see. So it is a linear combination of your input variable where x is a input vector, and so my input is in terms of vector where the different entries are from x1 to xt where input vector is of d dimension, right? So transpose is nothing but if you just apply transpose, it will be vertical, right? So you can't write, you just to save a space of vertical, you just put it into a linear and this transpose form, right? So this is how you see it, x1 to xt. But when you want to write it into a line, you just put a transpose so that you can put it in a row wise fashion. So if there is an input vector of d dimension, then you take a linear combination of all the dimensions along with the coefficients. You just put one separate coefficient w0 where x is not available just to take care of the bias, right? So in general, these are having some restrictions. This is a linear model, but if you use directly this linear model, what kind of a decision boundary they can give you? They can only give you a line kind of thing. If you are in the two dimension, this form of linear model will produce only a line, right? It will produce only a line. But if you have some data set which is not linearly separable, right? Which is not linearly separable. In that case, no line can separate these two databases to this data set. So you need a more than you need more general linear model which will give you this kind of a decision boundary. And how you can do that? You can project these small dimensions into higher dimensions, right? You can project either these dimensions to higher dimension, or you can project this same dimension from same dimension to same dimension, but such that the transformation will be linearly separable. And then you find out a hyperplane. And when you project back to this, you will get this nonlinear, you will see this nonlinear decision boundary, right? So this is known as like basis functions, right? So in basis function, um, what we do, we can we how what is basis function look like? How basis function look like? You just feed your x vector, right? So it is a vector now. I'm always writing x, and this x is nothing but it's kind of a vector. You feed it to some function. This function will give you some scalar value, right? It will give you some scalar value, and you just put that scalar value as like so I it will give you some scalar value s1, right? So if you are using more than two functions, more than one function, so let's say this is my first function, then I use my second function, I feed again my vector to this second function, I will again get some scalar value s2, right? So if my x is of d dimension, right? If x is of d dimension, then I have used my x. I have mapped my x using two different basis function to different two values s1 and s2. Now I can say that I have used a basis function of two dimension. So if you put this s1 s2 like this in a vector form, s1 and s2. So what you have done, you have used a basis function which is nothing a vector of a functions. You feed this x to this vector functions. Why I'm saying it is a vector function? Because this basis vector can be seen as basis 1, right? Basis 2. So here it is of two dimension. And you feed x to both basis function and you will get s1 and s2, right? So here in general I have used this basis as a vector, and which is a vector of a function. You feed x to each of the function and you get some scalar value s1 and s2. So somehow you are saying that you are mapping your d dimension to some m dimension, right? So here d, let's say here this is, let's say, 3 dimension. So you can take a 3 dimensional vector and just can have two basis function phi1 phi2 and feed it to it. So polynomial. So is there any question regarding this thing? What I am telling you right now?
So D and M are not necessary to be input, right?
D is a fixed const. D is fixed, like it is given in the data set. For an example, you are when data set you have recorded, you data set you have been provided with, it will be x comma y, right? So x can be of any dimension. So here x dimension is d. So you don't have any control over d. So it will be provided to you in a data set. But you have a control over m. So you can use any basis functions. For an example, just to make you clear, you have used polynomial functions, right? So what you do, let's say the input, the x you got is x comma y. So the x that the let's say that in data set you have x comma y, right? X comma y. So here x is univariate. Just to make you clear what you have done in your previous classes. So x is univariate. You feed x to different basis function, and these basis function are polynomial n type. So you first derive your first basis function phi 0, and you feed your x to it. It will give you 1, right? Then you take your second basis function phi 1. You feed your x to it. So it is 0, right? You feed your x to it. It will give you x only, right? It will give you x only. Then you take your phi 2, second basis function, and it will give you x square, right? It will give you x square. And in general, you take some mth basis function, right? You feed x to it. X is a univariate here, right? X is a univariate here. You feed x to it, and what you will get? X to the power m, right? X to the power m. So in polynomial curve fitting problem, you were using basis functions which were of this type, right? So every basis function, what it takes x, and it just project it to in some power projection. Like if you feed If it is a mth basis function, it will produce x to the power m, right? Here x can be vector also, right? Here x can be vector also. So what the example you have taken for curve fitting is, or sinusoidal curve fitting in previous classes, it was a univariate variable, but it may be in general a multivariate variable also. Any question? So what the advantage of basis function, that it will project your d dimension data into m dimension, where the data can be linearly separable. And if the data is linearly separable, you can find out a hyperplane, right? So always you generalize, always you see hyperplane as a line in 2 dimension and a plane in 3 dimension, and you generalize it for high dimension. So, so in short, we assume that data is linearly separable in m dimension, and then you are trying to find out a hyperplane. Fine. So rather than you have started with this form of model, then we said that they are having some because of this constraint, we cannot find out the decision boundary which is non-linearly separable. Then what you do, you project your x into some high dimension space using your basis function, right? Rather than writing x now, you are writing it in terms of a basis function. And this form is as it is now, just you have replaced x with phi x, right? And it depends how many basis functions you have used. So it is just a generalized form where you have used a basis function. So that's why it is known as linear. Linear why? Because it is just a combination of W transpose X. Basis, because you have used basis function to project X into some m dimension space. Why it is function? Because it is producing some scalar value and you're modeling it, right? You're modeling it. Modeling it with term, in what sense? You are modeling in, you're trying to find out a parameter W, right? And W is nothing but this, when you find out the value of W, it will give you the hyperplane, right? If it is a line, it will give you intercept and slope.
Sir, there are so many non-linear functions. So, like, what we should decide, like, while choosing that function.
Yeah, we will come to that part. We will come to that. Very nice question. So you mean to say, how do I know like what is the basis functions use, right? That is in short where your question is. Yeah, you can mute yourself now. Dheeraj, you have any question? You can mute yourself if you don't have any question. Dheeraj Kumar. Fine. So the question is, how do I know what is my basis function? What basis function should I use? Because there are so many functions which can introduce non-linearity. So the idea is to uh, introduce non-linearity as well as the projection into some other dimension space. So we'll see. First, I have discussed the polynomial basis functions, right? So polynomial basis functions are of this type, as we have discussed just now. They are global. They are global. A small change in x affects all basis functions. So it has some disadvantage. So polynomial basis functions have some disadvantage. And what the disadvantage is, just to refer, just for more clarity, I have just given you this hyperlink, right? You just go to this hyperlink and read it. In intuitively, I just what global means. For an example, you have used basis. You have used this expression for polynomial. It is W0 for intercept, and you used W1 for slope, right? And you want to fit a line to a data set. It means if you have used this parametric form, you want to fit a line to a data set. Let's say this was your data set. This was your data set, right? So you started with this. You started with this intercept. So W0 is nothing but this. And slope, you started with very minimum slope. It is, let's say, almost zero point 0.2, and this was your second function. When you add these two functions, the collective function which you will get is let's say this was this function with some intercept and slope. But you have not fit this data, and because you want to minimize error, you want to tweak one of the function. It means you want to tweak one of a parameter, and let's say you tweak W1. To tweak W1, you want to fit this data set only, and it means you are changing your slope. The the second, when you tweak your model or W1 to fit this data point, your resultant function will be this, right? Your resultant function will be this. See, in effort of fitting this point, you have just missed this point now, because the effect is global. If there would be some way you want to fit this data point, and it could have tweaked this way, and it just come back once it just tweaked in some local proximity, not global proximity, then your curve could have fit to the every point in a data set. It is just for your intuitive generalization that I have used only two polynomial expression here. One is constant W0, and other is a slope one, W1x. It doesn't matter if you just take in general W0 plus W1x plus W1x, W2x square, and so on. The moment you start fitting one of your point and you push it for one term, that one term will affect drastically to all other terms also, because it may over dominate it. And at first, where your curve was fitting to some data sets, some points, now because you have tweaked one of the parameter, it may not fit to those old previous data samples or points. This phenomenon is known as a global effect, right? So a small change in S effect in X affects all basis functions. So you don't want to do that. So hence this polynomial basis functions may not be always preferable, because they have some global effect in them, right? So what kind of basis function should I use then? The second kind of basis function is this Gaussian basis function. Gaussian basis functions say that if you have these data points, right, you use data, three basis functions, right? Let's say first basis function where the mean, it is like simple a normal distribution, right? It is not, so you just take for the first location, mean for the second location, because you're using three basis functions here now. Just to try, just trying to give you intuitive feedback set. Let's say you want to fit these up to these data sets, three data sets, three data samples. So that's why you have used three Gaussian basis functions, where mean is placed at the respective function. So let's say this was a variance, and it is very similar, right? It is very similar. Oops. It is very similar, because Gaussian basis function is having the same form, right? Now you want to fit it, right? So you have to multiply this basis function with some larger value W2, W1. So what it will give, it will raise the height of it, right? It will raise the height of it. Let's say you want to multiply it with 0.8 to decrease the height of it. And you want to multiply this with 0.5 to just make a 0.5 or height of it, right? When you do it and you add all these polynomial functions, this could be the resultant function that you will get. Oops, just a minute. This could be the resultant function that you could get. when you just adjust the W0 and W1 to it, right? This is how it may seems, right? But the good advantage is that each Gaussian basis function is local in the sense of affecting it. So if you multiply this with some infinity also, what will happen? It will just have a, this is the effective range of this basis function, and it will shoot like from here, it will shoot to infinity, and it will come back within the given range, right? It will come back to, because it was the effective range, it will come back till here, and from here onwards it will have the effect of the surrounding basis functions. So this is known as a local effect, right? So these basis functions are preferable over polynomial because Gaussians are having a local effect and polynomial having a global effect. I hope this things is clear to you. Can you write quickly yes or no for this? Very nice. So it is pretty much intuitive, and it is required to gain a feeling of basis functions, right? Then not only Gaussian basis functions, you can have any basis functions like sigmoid basis function. And if I want to say, like, if you know some electronic background, so Fourier like transformation also generates some basis functions where sinusoidal and cosine sine and cosines are like your basis functions, which you want to multiply with different magnitude to just give a resultant wave, right, or resultant signal. So in general, you can see any nonlinearity as a basis function which you want to add up in terms of a linear combination. So it is important, very, very important, a linear combination, right? So you are multiplying every basis function with some coefficient in linear terms. So you multiply this with W0, this with W1, this W2, and finally when you do when you just precisely taking W0, W1, W2, you can generate any waveform, right? You can generate any waveform out of it when you take a specific combination of W0 to WF, right? So this is all right. So from here onwards, I understand. Whatever I discuss, I feel that we have already transformed X using basis functions. So the every time rather than writing X, we will be using 5X, right? So rather than X, we will be using 5X. So it means we are using the transformed version of our vector, transformed version of our input variable, right? This is all. So you just to make just to feel it intuitively, you always see it as a in a some other dimension space, but it is still an input, right? How you come to that other dimension space is based on your basis functions. So in general, you can from here onwards, you can take that we are using some X which is projected into some other dimension space using basis function. But all theory will be same. Even if you have not projected, you just replace 5X with X. So it means you are using your X into the original dimensions only without projection, right? Okay. So far, so good. Now, once I have done that, this is my one of the favorite topic which I have, which is also yours from now, because you have done maximum likelihood estimation twice in this course so far in just 12 lectures. And this is again, I brought it back to you guys. Now I want to bring that same example what we have discussed at first. So we have a curve, right? That curve is having this form, right? It may be sinusoidal or it may be parabola, but it can be represented by yx and w. So there are x is a data. For every x, you feed this to w, right? So if you want to write it for a line, it is nothing but w transpose x. Yx is nothing but w transpose x, where w is a vector of w0 and w1. So it is W0 and W1, W0 and W1, and X is a univariate variable here, where first basis function is 1 and the second is identity itself is X, right? You take a transpose of it, and what you will get, it is nothing but W0 plus W1X, W0 plus W1X, which is nothing but a line, right? So here W, Y, X comma W, here W is a parameter, X is an input variable, and if you just take this parametric form, it's a line, right? So if this is your original line, you just take some X, right? When you feed this X to this YX, you will get this Y, this value Y. You add a noise epsilon, you will get this point. You take second X, you feed it to the line, you will get this Y. You add some noise, you will get this point, right? You take some other X, you feed it to a line, you get this value on the line. You add some noise and you get this value, right? So this is how we have done. We know this methodology already. So we are seeing our target variable in our data set, which is of form X comma T, right? Which is of form X comma T. This is my data set. X is an input variable, T is a target variable. I am seeing my target variable as nothing, but it is an underlying true function with some added noise to it, because it is an inherent characteristic of real world data where noise is being added already. What kind of noise is this? It depends upon my formulation, problem state. It depends upon my modeling. So here I have added a noise which is drawn from a probabilistic distribution. And this probabilistic distribution is nothing but it's a Gaussian distribution, which we have already discussed, right? So it is having a probabilistic distribution, which is a Gaussian in nature. So I am just always adding some noise to it, where the mean is nothing but a value of a line, right? So if you want to rewrite it, what you can write, so mean is nothing but a line. Mean is nothing but a line. You are taking some variance, right? So it is how much away you are from the mean, and you are drawing some value T. So you are drawing some value T from it, right? So this is your new T. This was your mean, right? So you are adding some T to it. So in short, you can rewrite this. You can rewrite this whole two expressions, which is having some meaning, into one expression like this. Like this. Is this clear to you guys? Or any problem here in understanding this? Yes, no?
So the n here is a Gaussian function.
And this n is, yeah, it is a notational notion of a normal function, Gaussian distribution. So here this is a mean and this is a variance, right? Any questions? Yes, okay, fine, very nice. Okay, if this is clear, that is really good for you guys and to me also, because it will help me to explain further concepts to you. Now I want to construct a likelihood function, and assuming independent identity distribution identity assumption, I need to multiply all the probabilities. So this is my data set, right? I assume this data set is generated from a line. I want to find out what is that line. To find out a line, I need to find out an intercept and a slope. And that intercept and slope is nothing but parameter W. which is a vector of form w0, w1. So in short, I want to find out w vector, right? I assume that w vector I don't know, but if it is somewhere, it would be seeing like this. And if it is the case, what is the probability of generating a data set from this line, right? So I assume this is a mean now. And what is the probability of getting this value from this mean? This is a mean for second x in my data set. What is the probability of getting this x? This is a mean for third x. And what is the probability of getting this x, right? So let's say, just to make you understand, I'm taking two lines. This is line 1. This is line 1. And I take line 2. This is my line 2. Which line is more probabilistically making sense to you guys? L1 or L2?
So L1.
L1. So let's see why, right? So if I take L2, for this same x, right? For this x, for L1, this was a mean, right? This was a mean. And from this mean, I have some Gaussian distribution. And what is the probability of generating this point is this probability. But for this x, if I take a L2, I have this mean. And if I generate for the same variance, beta inverse, this was a Gaussian distribution. And what is the probability of generating this point? It is almost 0, right? It is almost 0 here. So this probability P1, and this probability, because of this Gaussian of L2, let's say it is P2. P2 is far, far less than P1, right? And it is 0, almost 0. So if you would have only a single data set, single sample in a data set, that is this x, then this x will be more likely to be generated from L1 rather than L2, because the Gaussian that is sitting on the mean, which is defined by a line, is having a 0 probability of generating the point from L2, right? Is this clear? Is this clear?
Yes.
Right, right. So this is just for one point. What if I would have so many points or samples in my data set? So taking a line in general or a function in general, which is yx, and yx is nothing but it is a linear model, right? So I said that it is a linear model. It means it is of form W transpose phi x. Phi x, why? Because I have already projected into some other dimension space using basis functions. So my linear model, this is linear, right? Never forget it is linear. That's why the linear model imposed this constraint that the model look like W transpose X. So W transpose X is nothing. You can see it is a line in 2 dimension. So if it is a line, then the mean will be defined by this construct. And this is nothing but a variance. And you will see like what is the probability of generating a target point which is in your data set from this line. You calculate all the probabilities P1, P2, P3 corresponding to samples S1, S2, S3, and you multiply all those probabilities. Remember, my line is still a variable concept because I have not fixed my intercept and slope, or in general, I have not fixed my parameters W to W0 to Wm. So I can tweak my parameters and I can change my line every time. For every line, I can calculate the probability, and I want to find out a line which can maximize my probability. This is what we have been discussing, right? So rather than taking a likelihood function, which is nothing but the product of a probabilities, you take a log, and I have already explained it. So once you take a log, you get this form of likelihood function. So it is a log likelihood function where EDW can be written as this, which is nothing but a sum of square errors, right? So it is a log likelihood function. If you take a negative of it, so you want to minimize it because you want to maximize the probability. If you take a negative of log, you want to minimize it. So if you want to minimize it, it will bring this negative to positive, 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 negative, right? And if you this is positive, you want to minimize this, it means you are want to minimize the sum of square errors, right? This is also we have discussed it. Now I want to find it out what is that W which can maximize my probability. So I will construct a mathematical formulation for this model. So I take a gradient of a log likelihood function. So if I take a gradient of log likelihood function, what I will get? This is the form that I will get, right? So it is a calculus. I can do it for you, but I want you to just try your hands on this, right? So you will get this solution, right? And this is your phi matrix. So I will explain one by one very slowly to you guys. So I said that you had a data set x comma t, right? X comma t, x comma t. This is the form of your data set. You have used some basis function just to make you understand. Let's say it's a polynomial basis function. So you just first project your x to x0, which give you 1, then x to x, that will give you x, then x square, right? Then x cube. Let's say this is the only degree that you have taken m equals to 3. So you take all your x one by one. So you have 10 samples. So this is sample 1. So this is sample 1. Then you take your sample 2. Take first basis function as 1, sample 2. So this is x2 itself. Then this is x2 square, right? And this is x2 cube, right? And if you have 10 samples, so last row will be x1, sorry, 1, x10, as it is the 10th sample, then x10 to the square, because you are taking a second polynomial basis function. And the third polynomial basis function is x10 to the cube, right? X10 to the cube. So this is your phi matrix. This is the matrix that input was a univariate variable, but you have projected your univariate variable into 4 dimension, right? So this is your first dimension, which is always fixed. This is your second dimension. This is your third dimension. And this is your fourth dimension, right? So the matrix will be the dimension of a matrix. How many points you have in your data set? That is n points. And what is the projection? How many dimensions you want to project? It is of m, let's say it is of m minus 1 dimension. So then it is m dimension, right? Because 1 is fixed. It started from 0. So it is the matrix dimension will be n by m, right? This is phi. So now here onwards, you see that phi is nothing but your input variable, where the input variable has a dimension of input variable is of m dimension, right? So feel that phi is nothing but it is a projected x matrix where every row is nothing but a input sample. Yes or no? Is it clear? So it is a this is known as design matrix, right? This is known as design matrix, and you can see it as like an input where input x. So if you don't project it using basis function, then you can write it x as this, like x. In statistics, people write it as x, right? So let's see now from here onwards how to derive this solution. So you know what, this was your error function, sum of square error. I have used basis function, and because it is a transpose, right? I can rewrite this form as W transpose phi x. My fault that this phi is nothing but it's a vector, right? It's a vector. I will clear it. So this is a vector, right? So W transpose, and it is also a vector. So it should be bold as per my notation convention on PPT. So W transpose X, I am just switching my mathematical expression to a vector notation. So it is, I am just rewriting this summation, which is nothing but dot product into a linear algebra terms, and it is W transpose phi X, right? I have one more notation, sigma here. So I can rewrite this whole error expression as this expression, right? Where in general this phi I see as this phi I see as a vector of phi 0, phi 1, and let's till phi m minus 1, right? Phi m minus 1, right? And every time you feed your x to it, so it is a vector. So every time you feed your x to it, what it will give you? It will give you a vector of your value on line for every x. So if you have 10x, right? So this phi x, oh, this is the same matrix, design matrix, right? Which I have told you in previous slide. So this phi w, what it will give you? So this phi is nothing but first sample in projected space, second sample in projected space, third sample in projected this that was your phi, and you multiply this phi. So this is your phi. You multiply this phi with your w. So this is your vector w0, intercept and slope kind of thing, and this is till wm minus 1, right? Wm minus 1. So you are taking first row and taking a dot product with this w. It is nothing but it's what it is. It is x, right? It is your first sample. This is your second sample. This is your third sample. So you are taking your first sample, taking a dot product. It means you are saying where I am on line for my first sample. So this is my, I am where I am on line. So if you do x transpose w, you are here on line, right? If you take your second sample, you are somewhere here on line. And if you take third sample, you are somewhere here on line. So right. So phi w will not give you your values on that hyperplane or on line, right? And how much far you are from that line minus t, right? So if your actual t, so you are just subtracting it. If this is your t, you are subtracting it. If this is your t, you are subtracting it, right? So it is nothing but it is a 1 by 1 distance or error from a line which you feel that this is a line to the target variables in your data set, right? So we have written it as twice, right? So it is written twice. So it is error E1, E2, E3 for every sample. This is also the same error, right? But we have taken a dot product with itself. So dot product with itself is nothing. So if you take a dot product with x transpose x, right? So what it will give you? So x is nothing but x1, x2. Let's say there are two elements. So x transpose means it is row x1, x2, and x is a column vector here because it is x only, x1, x2. When you take a dot product, it is nothing but x square, x1 square plus x2 square, right? X1 square plus x2 square. So it means you are squaring every component of a vector. So this is a vector. You are taking a transpose with itself. So it means you are squaring every error and summing it up, right? Can you just nod your head on this? So it means you are squaring every error and you are squaring it. Very nice. Very good. So very nice. So I have written my error function in some linear algebra terms, and this is same half which we have taken from here, right? and somewhere this square will be cancelled by this half, right? So it is just for that optimization purpose we have taken this scaling factor. No need to worry about this half too much. So now my error function is this. What I do, I take a derivative of this error function with respect to my W. When I do this, I put it, the derivative it equals to 0. And when I simplify in terms with W, what I will get? I will get phi transpose phi whole inverse phi transpose T. It is the value of that W which is actually explaining more probabilistic to my data set. It means these W will give you the maximum probability of generating the data set. It's a maximum likelihood estimation, right? The good part of this formulation is whichever basis function you use, only your design matrix will keep on changing, right? If you use polynomial basis function, then it will be 1 x square x cube, this kind of thing. If you use a polynomial basis function, then only things will remain same and your design matrix will keep on changing. In the Gaussian basis function, this will be value v1 v2 if you have used 3 polynomial basis function, v3, but the construct of deriving W will be phi transpose phi whole inverse phi transpose T, right? I hope this is clear to you now, and I will wind my lecture, today's lecture here only, and I will start from the next concept. If you have any questions, please let me know, or you can ask me in the beginning of the next class. Thank you very much.